how intense she gets. Well, okay, and if you have no idea who I'm talking about, she's the one of the trainers in the Biggest Loser. It's like a weight loss show, and then she releases a whole bunch of fitness DVDs and stuff, and she's just so intense is the only word I can think of. All right, we'll pick up on chapter 5, and this is on sampling distributions. We're going to talk about sampling distributions, and we'll have our first application with chapter 6. All right. Okay, so sampling distributions. Last week we saw the normal distribution and the binomial distribution, or prior to that we saw the binomial distribution. We covered the rules of probability. Okay. This is kind of continuing on that. We're still dealing in the land of theory, the theoretical distributions and all of that. But the results of this can then be applied in a practical sense. Okay? And the idea is this. Whenever you see a sample, let's say your sample has 20 people in it, okay? And you calculate the mean of these 20 people. You're hoping that these 20 people are representative of the population. But really, you have no idea. You have no idea how representative they are. You're counting on the fact that they're kind of representative of the population. But you also know that if on another day you grab another set of 20 random people, the number you get there is not going to be the same as the number you have today. Okay. So when you get different numbers, how much of that difference can be attributed to just random variation? Okay. So we study sampling distributions. Sampling distributions talks about how samples can vary from one to another just on the basis of random selection. Okay. So how much do samples vary from one another because of random chance alone? So let's say we don't understand, not that we don't understand, but the math involved to solve this theoretically using equations is rather difficult. Okay, it can be done, but it's rather difficult. So instead, what if we wanted to kind of brute force this? So in the same way that if you had no idea how a coin worked, you can brute force it in terms of you just flip it a whole bunch of times, see how often it lands heads, and you get an idea, oh, it lands heads about half the time. Okay? We can take a population and we can just repeatedly draw a whole bunch of different samples, record the properties of those samples and compare them to one another, and then we get an idea of how much they vary. Okay? That's what we're going to pretend to do. Okay? So we have something that represents the population, we have a population, and we're going to draw out a sample. This is sample 1. Let's say it is let's just say it's of size n. Okay? And from sample 1, we record a y bar, okay, sample mean. X bar or y bar. So the mean of sample 1. And then we do do this again. Sample 2. Again, that's sample size n. So all of these samples, we keep the same sample size. And every time we do it, we record a sample mean. And we do this again. And do this thousands and thousands of times. Thousands and thousands of times. Okay. We keep track of all the sample means. Okay, the y bars. And then we create a histogram of all the different y bars. Okay. That histogram represents what we call the sampling distribution of y bar. Okay. So it shows us how much, what the most common values of y bar are. It shows us how much the y bars vary, and we get an idea of center, shape, and spread, okay, from the sampling distribution. All right, any inklings of what this would look like? So actually, we can use R to simulate this. So let's do that. Clear this. Okay. So I'm going to create something called a population. Alright, so what I'm doing is I'm creating a population with mean 100 and standard deviation 15. This is a random population, but normally distributed. Okay, so it's kind of like IQ scores. I think IQ scores have a mean of 100 and a standard deviation of 15. And my population only takes on full number values. Okay, there's actually, I got 10,000 numbers in here. Let me just do, these are the first 6 values, okay? So we have somebody, IQ 659, IQ 92, IQ 99, 99, 75, 79. Square bracket, bracket 1 through, these are the first 30 people listed in the population, okay? So we have a range of IQ scores, and I can create a histogram population, and my histogram looks like this. Let me add a few more breaks. Let's see, so looks like. Alright, so the population is very normal, okay? And we have a few people with extremely high scores, okay? So if we assume these were IQs, these are people with very high IQs, and these are some people with very low IQs. But most people are around 100, and within 2/3 within 1 standard deviation, 95 within 2 standard deviations, etc., etc. Alright. Let's say I take samples of 10 people out of this population. Alright, I can do that with this command. Alright, sample. Okay, so let me just, it doesn't really matter, but that's not what I want. Okay, so if I do sample population 10, it just says take 10 people out of the population, okay? What I do, just so these numbers don't disappear, because this, every time you call this command sample, it does a new random sample, okay? So just so these numbers don't disappear and I can actually work with it, I'm saving it into a variable called sample1, okay? But then because, so if I did this sample, and let's say I saved it into sample2, okay, if I do that, it actually, R doesn't tell me what you found in sample2. So the extra set of parentheses says, don't just save it in sample1, but actually show me what you saved in sample1. So the results of sample1 are these 10 randomly chosen people, okay? These 10 are actual people in this population. They're not, I'm not randomly generating any new, I'm not randomly making up numbers. I'm actually drawing 10 people out of these 10,000 people. And that's what I do here, okay? So I can find the mean of sample 1. And the mean of sample 1 was 95.4. And then I did sample 2, and the mean of sample 2 is 98.4. And I can do this again and again. I could say, okay, we'll take another sample, we'll call it sample 3, and tell me the mean of sample 3. Okay, and the mean of sample 3 was 93.7. Okay, just by happenstance, I happened to get means that were all lower than 100, but I could very well have easily gotten means over 100 as well. Okay, so you can imagine I do this thousands of times. Okay, with R, it's already kind of, I mean, I can hit the up arrow and that will save me a little bit of time, but I don't want to have to consistently do that. So I can write something, I can write a script, okay, and I'm going to create just a placeholder called sample.means, and the first, I'm just putting in the value 0 here, but I'm just creating kind of a placeholder. This is where I'm going to store my values, and I'm going to create a loop, okay, and a loop, it's I don't know, it's a functional, it's a computer thing. How do you describe a loop? Basically, all I'm saying is I'm going to do the same set of commands over and over and over again, okay? Because that's what we're doing, right? We're just going to reach into the population, pick out 10 random people, find the mean of those 10 random people, and record them. I'm going to do it again, and I'm going to do it again, and I'm going to do it again, okay? So I'm saying this is the counter, so it says I 1 through 10. So this just means do it 10 times, okay? And what we want is take a random sample of 10 people from the population and just call it X. But we can call it sample, we can call it the sample, whatever we want, okay? So X is going to be 10 numbers, just like sample 1 was, sample.2 was, 10 numbers, okay? And I'm telling it I'm telling R to actually show me what those 10 numbers were and show me what the mean of those 10 numbers are. Okay, these are unnecessary steps. Okay, but I'm doing this so we can see what happens in the first 10 trials. And then I'm going to just bump this up to like 1,000 and hide and comment these out so it won't run these because I don't want to see a whole bunch of these things. Yes?
Okay, maybe I missed it. What does the I stand for when you say put it in
The I is a
unit?
counter, okay?
Okay.
It's when you run a loop, okay? So if you go to the school track and field, I'm losing my mind here. If you go to the track and I say, okay, just run on the track, you run in a loop and you could potentially do that forever, right? But I say, okay, well, count how many laps you do, and when you get to 10, stop. That's all I'm doing, okay? So there's just inside the computer's brain, it's saying, okay, I ran this once, I ran it twice.
Oh.
Okay, I got to 10, now I can stop, okay? It doesn't have emotions or stamina. I mean, it does have memory, so it might run out if you use a billion. But you can say like, okay, we'll do it 1,000 times or 5,000 times, and it'll do it, okay? And over here it says, so you get it, it prints those out just so we can see what it's done, and then right here it says sample.means, which is that placeholder thing I've done, and this bracket notation tells you you can indicate where you want it, okay? So just imagine you've got a sheet of paper with a bunch of rows numbered, and you can say, okay, well on that first row, so when I is 1, so that's after your first lap, on the first row, write down the mean of x, okay? When I is 2, in the second row, write down the mean of x after the second time you did it, okay? And just do this for 10 times. And so at the end of this, sample means will have 10 rows filled out, and it's a vector, so there's no rows, but 10 numbers filled out. Okay, so I'm going to just highlight this. I'm going to run it, okay, and it'll just go boom really quickly. And we can see what it did. Okay, so the formatting looks terrible, but so it did this 10 times. The very first time, these were the 10 people it selected, and the mean of these 10 people was this. The second time it did it, these were the 10 people, and the mean of those 10 people are this. And this third time, these were the 10 people, and the mean of those 10 people is that. Okay? And so I recorded 104.5, 97.8, 91.7. Okay, these are the 10 numbers I recorded, and I can check sample.means, and indeed, it shows me the 10 numbers that sample.means recorded. Alright, so is everyone following what we're doing here? Kind of? Okay. So all I'm doing is, this is the population, drawing 10 people out, taking the average of those 10, and then, okay. So, we did it 10 times, now I'm going to ask the computer to do it, 1,000,000 times, or whatever, it doesn't matter. Okay? Maybe we'll have it do it 500 times. Okay? So, I'm going to say, but I don't actually want to see it print out the 10 people it selected or the means of those, okay, because I'll get that at the end. So I'm putting whatever this symbol's called, pound sign, which says ignore this line, okay, and we'll do it 500 times. 500 samples of size 10, okay. Did I mess something up? Oh, okay, no. Alright, so I can do sample.means, there's 500 of them, and now I can make a histogram. Alright, so any guesses what this histogram is going to look like? So I've got 500 numbers. Sample.means, okay. The population just said, what's that?
So wouldn't it just be it's just the same?
It would look just like the population? Okay. Alright, so pay attention, it's gonna feel like it looks exactly the same, but pay attention to the horizontal axis, okay? So here we said, you know, 2/3 are within 1 standard deviation and 95% is within 2 standard deviation. So the middle 95% go about from, if you're eyeballing, around 70 to around 130. Okay? When I create this for histogram sample means, it looks kind of similar. Let's add some breaks here. Let's make it a little. So this is probably a result of it being only 500 and not like a million. Okay, but this kind of gives you an idea of the sampling distribution, and we already see that the spread is very different here. Okay, whereas before it went from 70, 90, the middle 95% were about from 70 to 130. It seems like the middle 95% would be about from 93 to 107 or something. Okay, so the spread has changed. Okay, the shape doesn't look, it looks considerably different at the moment. But if I were to run this, let's say, many more times, the shape would okay, so it's actually
Is it the emergency button?
it's thinking. Okay, it says 50,000 laps. That's a lot of running to do. Okay, but it finished. Okay, and we'll say, okay, well, good job. That. Okay, so this is like very normal. Okay, and so the spread seems to have changed a little bit, but I mean, like we get more in the tails now. But we can see that the middle 95% is probably still like 90 to 110, okay, or something. Maybe even a little bit. Yeah, it might even still be 92 to 108 or 93 to 107, something around there. Okay, so we have this nice normal shape thing. Okay, is that okay? Any shocks or surprises there? Okay, so what we notice is that the spread has changed. All right. What would happen instead of taking samples of size 10? What if I took samples of size 40? What do you think would happen? Huh?
We lose more of the extremes.
Yeah, well, let's see. Okay, I'm not gonna have it do 50,000. I'll just have it do 10,000. Okay, so it doesn't get angry, but it'll still take its time. Oh, that was quick, actually. All right.
So how do you know when it's finished thinking? The stop button.
The stop button goes away. Okay, and then and this little what do you call that? That indicator appears. Okay, and says I'm ready to accept more commands. Okay, so here it is. Sample, that means breaks 30. Oh, it looks exactly the same. Did I screw something up? Oh, I know. I have to delete the old sample means first, because it just rewrote the first 10,000 lines of sample means is what happened. Okay, and then there's still like lines 10,001 to 50,000 that were exactly the here it is here. And we do see the spread has changed also, okay? So now we're going, the middle 95% really goes from 96 to 104 or something around there, okay? Alright, so what's happening? Well, I'll tell you. Yeah, as we increase our sample size, the standard deviation of our sampling distribution, okay, that's like a complicated thing. The standard deviation of the sampling distribution gets smaller as the sample size increases. I'll write that up on the board, okay? We call that thing the standard error as sample size increases. What do you think would happen? So this was with a population that had, the original population was normally distributed. Okay. What do you think would happen if I have a non-normally distributed population?
Sample would be one.
Okay,
Normal?
so let's
So just random, like just randomly distributed.
let's say I've got okay, let's just make up a crazy distribution here. No, that's not. Okay, let me do I'm gonna call this population 2, and let's do R by gnome. We'll ask for 40,000 size 8 and probability point 7.
Can you?
So let's okay. So this is my histogram here. Okay, it's a binomial distribution. So I only have whole numbers, and 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the labels are all funny here, okay? But this represents, so this was if I don't know. It's a binomial thing where I've got probability of success 0.7, and I'm doing this 8 trials. Okay, so I can get any number between 0 and 8, 0 and 8, whole number only, okay? So I'm either going to have 0 successes, 1 successes, 2 successes, all the way up to 8 successes, okay? So it's not continuous, so it's clearly not normal. And even if we were to approximate it, it would look like it's skewed left, okay? The mean would be around what? The highest, this is 876, so the highest peak is at 6 and 5. But the mean is would be n times p 5.6. Okay. So this is population 2. It's not normal. So just imagine having, when you reach in there, you're only going to get a whole number between 0 and 8. It's got this distribution here. Okay. So if I did a sampling distribution here, so I've got a jar, a whole bunch of slips of paper, either has a number 0 through 8 distributed like this, and let's say I take 10 numbers out, okay, and I figure out the mean of those 10 numbers, and I do this over and over and over again. What do you think my sampling distribution will look like?
It would be more skewed.
Okay, well let's see. Okay, so we'll do population 2. We'll just take 10 numbers out at a time, and so just so we can see what maybe doing this 10 times might look like, I will print out the actual 10 samples that we draw. And I'll just do this very quickly. Okay, so you can see I'm drawing a whole bunch of 6s and 7s and 5s, and And I'm getting numbers like 6.5, 5.8, 5.7 as my mean here, okay? So that's okay, right? Okay, so let's do this a bunch of times. 10,000. I don't want to actually see these things. Oh, and let me delete out sample means. Okay. So I'm going to run that. There it goes. It's finished. Okay. Histogram of sample means. Alright, here we go. What does it look like? That's that. Let's increase our breaks. What does that look like? It looks pretty symmetric. It looks pretty normal. Yeah. And we're getting an average between, I don't know. So the middle is around between, 4 something and 6 something. And the center is right around 5.5, 5.6. Okay. As we might expect.
When you do the R binom, so does that mean you're rounding? You're using the whole numbers? Is that what you mean? Because I'm not understanding the R.
Oh, the R means randomly generate from a binomial distribution. Okay. So you have the P binom and D binom and P norm and Q norm. Those are all calculations based on the underlying distribution. R also has a function with the R and it says randomly generate numbers from this distribution. Okay, which is useful in simulation studies. But I didn't have you guys do any of that. Okay, so let's try that again. Let's increase our sample size. Well, actually, let's decrease it. Let's take samples of size 3. What do you think our thing would look like if we had samples of size 3? So the underlying binomial, again, is looks like this. The underlying binomial one looks like that. And when we did samples of size 10, it looked like that. And let's see what samples of size 3 look like. It looks funny. It looks funny. So we see, and it's, I wonder, can I color it somehow? Maybe I need to change my breaks to this. This is as good as it's gonna get. Okay, so it looks funny. And what's going on is because of this breaks thing. So we can see it's kind of normal-ish, but we're also getting gaps here and stuff, okay? So what's happening is that when I take samples of 3, and I take the mean of those 3, and the numbers that are going in are only whole numbers. So maybe I get 776, okay? The average of those 3 will have a 0.333, or a 0.666, or a whole number, okay? So that's why I'm getting these gaps here, right? Actually, the same thing happened when I took samples of size 10. I always had a decimal that either ended at 0.1, 0.2, so on and so forth. But they merged together. And here the skew, I don't know if you can see it, but there is still a little bit more of a skew here than there was with samples of size 10. Okay, and then if I increased it to samples of size 40, any of the skew that was in the original underlying binomial distribution here would almost completely disappear, okay, if I increased it to samples of size, or even 30. If I did this and ran it, the skew would almost completely disappear. Let me just, now I'm getting another artifact of having something strange going on. Okay, the skew here, I mean maybe a tiny bit shows up right here. Okay, but the skew is pretty much gone, and then we see also that the spread has decreased. Okay. All right, so all of this simulation stuff, just to kind of make the point of, you know, how sampling distributions work, we're just drawing samples of size n repeatedly out of a population and keeping track of each sample mean that we get. All right? And what we see, what we have observed, okay, so the first one, okay, so first few examples, we had a normal population. Okay, and then when we had sample size equal to 10, okay, the sampling distribution appeared normal. Appeared normal and had a smaller spread. Okay. We increased 10 to 40, and the sampling distribution was still normal, and had even smaller spread. Then we tried it with a binomial distribution. Okay, so this was not normal. As a population. Okay. Sample size 10. It actually appeared kind of normal. It appeared pretty symmetric. Okay, and spread was less, centered close to 5.5. Okay, it was binomial distribution, sorry. N equal to 8 and P equal to 0.7 is what I did for the binomial distribution. Okay, and then when we had the sample size down to equal to 3, which is right, N 3. Okay, a little bit of skew. Okay, more spread than n equals 10, but still centered around 5.5. And then we bumped it up to 40 and stuff. There was hardly any skew. Seemed very symmetric. And the spread was very small, centered around 5.5 also. Just copy that down. Alright, so to summarize, so all of this actually matches up very closely to what the math and the theory says. Can I erase this? So this was all from empirical observation, right? We did it on the computer, okay? This matches up closely to theory. And this is actually the central limit theorem. Okay. Which basically says if you do what we did, so you have some population with mean equal to mu and standard deviation equal to sigma, okay? The shape doesn't matter, whether it's discrete, continuous, skewed, symmetric, okay? Shape doesn't matter. Okay, so you've got some population, and then you draw random samples of size n. Okay. This is, okay, I'm going to put in the statement which is if n is sufficiently large, n is sufficiently large, looks like his, but n is, so if the sample size is sufficiently large, then the sampling distribution of y bar will be approximately normal and approximately normal means for all intents and purposes we can treat it as normal, okay? But, well, I shouldn't say that. Okay, will be approximately normal with mean equal to mu and standard deviation equal to sigma divided by the square root of n. Alright, and so that's why when we increased the sample size n, we saw the spread get smaller and smaller and smaller, okay? Because the standard deviation is the standard deviation of the original population, sigma, divided by the square root of n. Okay, so what does sufficiently large mean? that means if, so there's two parts. If the population is normal, then any n is sufficiently large. So if the population is normal, any size n, whether you're taking samples of size 1 or samples of size 50 or samples of size 3, any size sample is large enough for the central limit theorem, this part, to be true. Okay? But if the population is not normal, n must be larger. and this is very vague. Must be larger. For most situations you encounter in real life, n equal to 30 is usually big enough. N equal to 25, 30, usually big enough for most situations. Okay. N equals 25 or more. Some will say n equal to 30 or more. Doesn't matter. Is usually big enough for most applications. So if you take samples of size 30, then you can use this sampling distribution as normal, even if your population is not normal, binomial, skewed, whatever it might be, okay? But if your population is extremely skewed, or something else is going on, n equal to 25 might not be big enough, okay? In extreme cases. And in those situations, it might be better to transform your data, like you take the logarithm of all of those numbers or something like that. Okay. Yes?
What would be an example of an extreme case?
Maybe income data? Okay. So income is extremely skewed, right? You have most people making, I don't know, between 10,000 and maybe 150,000 a year. Okay, that covers like 99%, right? But that top 1%, they could pull in literally 10 times or 100 times someone else. Okay, you got people making $1 million, several million a year. Okay, and that's going to be extremely skewed if you regraph that. Okay, for celebrities with who's the TV stars, they get paid a lot and stuff, so their salaries are big, or athletes 20 million a year or something. Very a lot. So that's gonna mess that up. So sample size of 25 will not help, right? If you happen to select someone like that in your sample of 25, then your data will be extremely skewed. All right, let's take a short break.